In this lecture, we are going to see the second transformation technique for a continuous random variable x, and this technique mainly based on the theorem 2.8, and this theorem tells us that under some conditions the random variable y, which is g of x, is continuous, and the PDF can be calculated using this formula. Okay. So what are the conditions? The conditions are that x be a continuous random variable with PDF fx, support sx, and the first condition is that, okay, first condition is obviously x is continuous random variable. Second point, I need that support of x is an interval in R. Then I have a function g, which is from support of x to R, which is from support of x to R, and this function has to be a differentiable function. Then the derivative is either negative or positive for all values of x in the support. Okay, so combination of positive negative values of the derivative are not permitted. So if this condition satisfies, then this theorem tells us that g of x, which is y, is a continuous random variable, and the PDF of y can be calculated using this particular formula. What is this formula? The formula is very easy to remember because you see that this formula is very almost same as, actually same as that we are used during the transformation of the variable in integration. Because this quantity you can think as of Jacobian, one dimensional Jacobian, and this one is basically f of x at the point x, but here x is basically nothing but g inverse of y. That's why basically f of x at the point g inverse of y. Natural question is that why g inverse exists? Answer is straightforward, because the derivative is either negative or positive. That means g function is strictly monotone over the support, so the inverse exists. So this theorem essentially tells us a set of sufficient conditions for y to be continuous. Obviously, if these conditions are not true, we cannot say what kind of random variable y will be. It could be continuous, it could be discrete, it could be neither continuous nor discrete. We will see some of the example of that nature. Okay. So again, repeat the same thing, that well, the conditions are x is continuous, support is an interval, g is a differentiable function, and g prime is either negative or positive on the whole support of x. Okay. In that case, y is continuous, and the PDF is given by this expression. Let us see some of the examples. Proof I am skipping because this is again coming from, as I already mentioned, it is coming from the technique of integration, that variable transformation technique of integration. So it is a straightforward application of that. I am not going into that. Let us discuss some of the examples where we can use this theorem to find out the probability density function of a transformation of x. Okay. So first example is x follows uniform 0, 1, and we take the transformation is minus log x. Okay. And log x is basically a strictly increasing function. So minus log x is strictly decreasing function. So clearly we can check all the condition of the previous theorem. First condition was that the support of x has to be an interval. That is true, because for a continuous, for a uniform 0, 1 random variable, the support is the interval 0 and 1. Okay. Next condition was gx is a differentiable function, log x is a differentiable function, so minus log x is also a differentiable function, and it is easy to check that the derivative of minus log x is negative on the interval 0 to 1. So now all the condition of the previous theorem hold true. That means I can tell that y, which is minus log x, is a continuous random variable, and now I can find out the probability density function of y in terms of the probability density function of x using this formula. But to do this, first I need to find out what is g inverse of y, and it is easy to see that what is g inverse of y from here, which is nothing but e to the power minus y. So plug in e to the power minus y here, and when I take the derivative, that turns out to be minus e to the power minus y, and because of this mod, it turns out to be e to the power minus y, and fx at the point e to the power minus y is 1 if y is greater than 0, and it is 0 if y is less than equals to 0. So that's why the density function becomes this. Note that the random variable x, this PDF is basically PDF of a exponential distribution with parameter 1. So the random variable x follows a exponential random variable, exponential distribution with parameter 1. Okay, so y is a exponential random variable with parameter 1. Let us take another example. So example 2.35, we start with now the example. In the previous one we could get exponential, so we start with the exponential now. And suppose we talk about y equals to x square. Notice that y equals to x square is not 1 to 1, and if you take the derivative of y equals to x square on the negative part of the real line is negative and positive part of the real line is positive. But as the theorem says, we do not need to talk about the whole real line. We have to only talk about the support of x, and in this case the support of x is 0 to interval 0 to infinity, the positive part of the real line, and on the positive part of the real line the derivative is strictly positive. So the conditions of the previous theorem hold true. The support is an interval, g is a differentiable function, g equals to x square is differentiable function, and the derivative is strictly greater than 0. So that means that y equals to x square is a continuous random variable. I need the inverse transformation, and because y is only positive values y can take, and x, the support of x is also positive, so the inverse transformation in this case the positive square root of y. G inverse of y is the positive square root of y, because support is the positive part of the real line. Now I can write the PDF of y very easily. It is nothing but the density function of exponential 1 at the point root y, which is e to the power minus root y, and then I need to take the absolute value of the derivative of root y, which is 1 by 2 root y, and this is true if y is strictly greater than 0, and otherwise it is 0. The strictly greater than 0 is coming from the fact that, well, your x has to be strictly greater than 0 to have the density function of x is strictly positive, otherwise it will be 0. So strictly greater than 0 is coming from that part. And so I have this density function, and in this case I can use the theorem easily to find out the density function. Okay, let us talk about another example. Now instead of the exponential in the previous case, we take it is a normal 0, 1. Now when we take it normal 0, 1, the support is the whole real line, and on the whole real line the derivative is positive on the positive part of the real line and negative on the negative part of the real line. So clearly the previous theorem we cannot use, the theorem 2.1 we cannot use here to find out the probability density function or probability mass function, whichever applicable to y. So what we can do? Obviously we can use the technique 1 to find out the distribution function, because this distribution function exists for all kind of random variables. So technique 1 we can use for all kind of random variables, but the thing is that sometimes using the technique 1 is difficult compared to the using of the technique 2. That's why we sometimes use the technique 2. Okay, but in principle technique 1 can be used in all the cases. Okay, now if I use the technique 1, you can check the distribution function of y turns out to be this one. This one is very easy to check. I left is an exercise. So you can check the distribution function of y equals to x square turns out to be this one. And the idea is exactly the same. We have already done it, this kind of thing before. So that's why I leave it as an exercise. Now in this case you see that if I take small f to be this function, then this capital X can be written as the integration of small y t dt from minus infinity to y. So that means the corresponding random variable y in this case is a continuous random variable. So this is one of the examples where one of the condition of the previous theorem does not hold true, but the random variable y is a continuous random variable. So as I mentioned earlier, that not satisfying some condition does not mean it is not a continuous. So it is one of the examples where we have seen that this is not a continuous one. On the other hand, if you see the example, one of the example we have already discussed during the technique 1, which is basically x is exponential, and we talk about y equals to box of x. In this case, again, you see that the function is not differentiable function because I have jump in the function, I have discontinuity in the for box x function. So this box x function is not differentiable. So one of the condition of the theorem do not hold true. And in this case, we got that y is a discrete random variable. So my whole point here is that, well, this theorem 2.8, is basically tells us some sufficient conditions so that y is a continuous random variable. If this condition do not hold true, the corresponding random variable could be discrete, could be continuous, could be any kind of random variable. We need to check it by some other means. What kind of random variable the y is if these conditions are not true, if the conditions of theorem 2.8 are not true. Okay, so with that I stop in this lecture. In the next lecture we are going to see the expectation of function of random variables.